Good day and welcome back. I am excited to say that we are finally ready to begin our discussion on integration. But before we dive into this idea of evaluating and interpreting a double integral over a rectangle, let's go ahead and give ourselves a quick reminder of how we interpreted and developed a single integral back when we were in Calculus 1. And the question that we are asked is, if we were to consider the curve y equals f of x that we see, how much area is enclosed beneath that curve y equals f of x as we let x vary from a to b? So somehow what we wanted to do was come up with an approximation. And the idea itself was actually very simple. We said we can't just directly calculate this area. It's not a common geometric shape with some related formula for its area. Instead, what we do is we break it up into pieces that are familiar so that we can somehow approximate it. And the idea is we said, how about we take this interval from a to b, and typically we say let's break it up into n equally spaced subintervals. We would call a x naught, and then we have kind of an x1, x2, x3. There's kind of what happens in general. Then way over here we get to xn, and the idea is that we've taken the interval from a to b, and each little subinterval has a width given by delta x equals b minus a over n. And then on each of these little subintervals, what we can do is draw an associated rectangle. The only decision we have to make is decide how do we want to determine the height of the rectangle. And a nice convenient thing is just to say, how about we go to the right-hand endpoint, go up to the curve, and we'll use that as the height of our rectangle. So with that in mind, if I draw in several of these just to illustrate the idea, we have one rectangle, a second rectangle, a third rectangle, kind of this generic rectangle, and then the final rectangle, and there's a whole bunch in between. But the idea is that a rectangle itself is very easy for us to find the area of. For the average rectangle, we would typically represent that as the function value at a point, maybe x sub I is the right-hand endpoint of the ith subinterval, times the width. And when we have it in this form, we're clearly seeing that area formula of a rectangle, a height times a base. And what we have to do is just make sure that we add them all up. So we would go from I equals 1 to n if we are adding up n of these rectangles. And this is something that we referred to as a Riemann sum. Now the common question your Calculus 1 and or 2 instructor probably asked is, at this point we have an approximation to that enclosed area. How can we make it more accurate? And the idea is the more rectangles we use, the closer our approximation becomes. And if we want to make it exact, what we can do is use infinitely many rectangles, which essentially means take a limit as n goes to infinity. And when we take the limit as n goes to infinity of this Riemann sum, what results is the definite integral. And recall that the reason we go through this kind of development of the definite integral is not to bore our students, but instead is to make sure that we have the geometric interpretation. We are calculating an enclosed area. And a bit more precisely, I'm going to describe this as being a net difference of enclosed areas. And the reason I'm being a bit more precise is the generic function I have drawn to the left is always positive, which means it truly is an enclosed area. But if that curve dipped below, you would have to take the area enclosed above the x-axis, subtract away the area enclosed below. And let me try to illustrate this idea a bit more clearly via GeoGebra. And here's just a small clip of a GeoGebra file. We have a curve. We're using two rectangles to estimate how much area is enclosed under the curve. And what we'd like to observe is just as we use more and more rectangles, we get a better and better approximation. And for some reason, I can never make my pictures on the board or the screen illustrate the idea as clearly as we can see it in a GeoGebra file. And before diving into the double integral, I do want to note that this interpretation of a net difference of enclosed areas is an extremely important idea. That there are certain examples that a Calculus 1 student thinking about this interpretation of enclosed areas can evaluate much more quickly or efficiently than a Calc 2 student would using some more advanced methods of integration. For example, let's consider the definite integral from 0 to 1 of the square root of 1 minus x squared. As a student who has recently finished up Calculus 2, there may be a certain technique of integration that you're thinking of. This is something that would be highly conducive for a trigonometric substitution. But that's going to require a bit of work, probably a half a page or so. Instead, let's think about this from more of a geometric perspective. That is, let's sketch a graph and think about how much area is enclosed. The graph would be given by y equals the square root of 1 minus x squared. And to visualize what the graph looks like, it's probably worth manipulating this equation algebraically. If we square both sides, we would have y squared is 1 minus x squared, or adding x squared to both sides, we see that we have the equation of a circle centered at the origin with radius 1. Now make a few observations though. What portion of this circle do we have? Our x values are varying from 0 to 1, so at a minimum we're to the right half of it. But also note that the y values equal a square root, which must be positive. So it's not the entire top half of a circle, but the top right quarter of a circle. And this area, call it A, is equal to the value of this definite integral. And we have a nice convenient formula. The area of a circle of radius 1 is simply pi, and we have 1/4 of that circle. Hopefully this example illustrates the power of having the geometric interpretation of the definite integral. Our goal now is to take this idea for functions of a single variable and extend them to our Calculus 3 setting, where we are currently dealing with functions of two variables. So let's go ahead and see if we can visualize the scenario. So we are going to investigate a function f defined on a rectangular region AB times CD. And note that the x here is not a cross product. The first interval is telling you where you find the x values. The second interval is telling you where you find your y values. So we have our x values restricted between A and B, and our y values restricted between C and D. And in the xy plane, this is really describing for us a rectangular region, which would play the role of the domain for the function f, and I'm going to try to sketch a generic surface representing f sitting above our rectangle. So sitting directly above the rectangle, we have some portion of the surface given by the graph z equals f of xy. And this says set the stage for the question that we want to answer. So the big kind of goal that we are going to move on to is, can we approximate, now it's going to be the volume enclosed below the surface representing the graph of our function f, but simultaneously above the z equals 0 plane. And note, this is the analogous question to what we asked in Calculus 1. Instead of finding, say, an enclosed area, we're now looking to find an enclosed volume. And in a nutshell, let me give you kind of the idea of how we go about this. We take our rectangular region, AB times CD, and we break it up into a bunch of little subrectangles. And then the idea is on each one of these little subrectangles, we can draw something up to the surface, which would be a rectangular prism. And even though we might not be able to directly calculate the volume all at once, we can approximate it by adding up the volumes of these more manageable pieces. And then in terms of our approximation, we're going to use that to get the exact volume by taking limits, much like we have done previously. And once again, to kind of help visualize this scenario, GeoGebra can be extremely helpful. So I'm going to play a small little clip and just kind of talk over it a bit. We have this surface in orange, and what we would like to do is somehow approximate how much volume is enclosed underneath this surface and sitting above some rectangle in the XY plane. So we've taken the rectangle and we've broken it up into 4 little sub-rectangles. And the idea is we see that we get an okay approximation to that volume. Clearly there's a lot of error involved. So in order to get a better approximation, we can use more rectangles. And in fact, the more rectangles we use, the better our approximation will become. So let's go ahead and work out a few details. In order to estimate this enclosed volume, we're going to take the same approach that we took back in Calculus 1. And I'm going to work through some of these details. It probably feels like a lot of them, but the idea is I want to give you enough information that we see where things come from and we've developed the proper interpretation. So what we're going to do is take our domain of interest for the function, this rectangle, and we're going to break it up into a bunch of little subrectangles. So first we're going to take this x direction and we're going to break it up into m subintervals of equal width. That is, we'll take this interval, we'll break it up, and then we're going to introduce some notation. Just like we did earlier in this video, we'll say a is x naught, then x1 would be the right-hand endpoint of the first interval, x sub 2 the right-hand endpoint of the second subinterval, and so on with m of them. We now do the exact same thing in the y direction so that we can force a grid over our rectangle of interest. So we break that y direction, CD, into now n subintervals of equal width, where this delta x should really now be a delta y. And now that we've broken up both the x direction and the y direction, we use this to place a grid on our rectangle. And I've tried to indicate that I haven't drawn the entire grid by putting small little dots to indicate where grid lines have been omitted. But once we have this grid superimposed on our domain of interest, what we're going to do is concentrate on one generic rectangle. I'm going to go ahead and call this rectangle R sub ij. The I sub j coming from the fact that it's the ith subinterval in the x direction, the jth subinterval in the y direction. So notationally, this would be given by the interval x sub I minus 1 comma x sub I times y sub j minus 1 comma y sub j. And I'm going to focus in on this upper right-hand corner of it. That is going to be the point given by x sub I comma y sub j. So once we've placed this grid, we've really created a bunch of little subrectangles. And note that's very technical. So a bunch of subrectangles. And note each one of these little subrectangles has the exact same area. And we will denote that area by delta A, and it would be its width in the x direction multiplied by its width in the y direction. And now, just like we did earlier, we are going to estimate this enclosed volume. So if we focus in on our subrectangle R sub ij, we could estimate the volume enclosed below our surface and above that z equals 0 plane. It would be given of the form a height, so think f of x sub I, y sub j, we're using our function to get the height, multiplied by the base. So similar to that observation from earlier, we can say height times, now it's a base area, but that will give us a volume. And that approximates the volume sitting above this one little subrectangles. And the subtlety is that we have a whole bunch of these rectangles to add up. And we have to really think about how many they are in terms of both the x and the y direction. So in terms of the y direction, we have to let our j values vary from 1 to n. And in the x direction, we have to let our I values vary from I equals 1 to m. And as we'll note in our next video, this is something that we refer to as being a double Riemann sum. And once again, I'm not trying to show you each and every little detail, but just enough to really develop this double integral. So now the double integral of the function f over the rectangle R is defined to be that enclosed volume. We've approximated it. If we want to make this exact, we just need to use more subrectangles. So how many more? Well, as many as we possibly can. So the limit as m and n both simultaneously go to infinity of the sum from I equals 1 to m, j equals 1 to n, of f of x sub I, y sub j, delta a. And note what this quantity is really calculating for us. I'm going to refer to this once again as being a net difference of enclosed volumes. That is, it's calculating how much volume is enclosed above the rectangle R, and we subtract away the amount of the volume enclosed below the rectangle. And this observation of a net difference of enclosed volumes is maybe the most important part of this initial discussion. And in the remaining videos, we will investigate how we can approximate one of these Riemann sums, first quantitatively, and then we'll sketch the surface of another function to see if we can actually calculate precisely what that enclosed volume or value of the double integral will be. So stay tuned and take care.